Okay, so as I mentioned in the previous video, we're going to make things slightly more complicated by adding some square roots, and then we'll also do a tangent in this video. So let's go ahead and take a look at this problem. We're going to remain in quadrant 1 for now, just so we can focus on kind of simplifying square roots and what we're going to see in Delta Math. So what I would like to have us do is determine, let's do sine of u plus v this time. And we're going to say tangent of u equals 2/3 and sine of v equals 5/7. So these ones are not going to turn out to be Pythagorean triples. We're actually going to have some square roots when we do the Pythagorean theorem in these ones. So the first thing to do is really just to point out that we already have the formula. So sine of u plus v is just sine of u cosine of v plus cosine of u sine of v. So what this ends up turning into is we now have a triangle u with 2 and 3. Tangent is opposite over adjacent. I mentioned this when I was writing it out, but I'll also write this down. These are both going to just be in quadrant 1, so I don't have to worry about plus or minuses. And then for sine, I have opposite and hypotenuse. So using the Pythagorean theorem, we have the square root of 9 plus 4 is 13. And then over here, we're going to end up with the square root of 24. So this is the square root of 7 squared, 49 minus 5 squared, 25. So we do in fact get 24. Okay, now here's the issue. Square root of 24 is perfectly reasonable. That is the actual answer. But oftentimes, as mathematicians, we like to kind of write things in a simpler way, and we like to take bigger numbers and reduce them to smaller numbers. And with square roots, we haven't really dealt with this year, but you might have seen it in a previous year. As a reminder, with a square root like 24, you could rewrite this as 4 times 6, and the square root of 4 is just 2, so this is actually going to be 2 times the square root of 6. And if you plug this into a scientific calculator, you would actually get 2 times root 6. So we're going to deal with kind of this simpler version right here, rather than the whole square root of 24. Square root of 13 doesn't do anything because 13 is just 1 times 13, and there's no perfect squares we can take out. Okay. All right, so let's go ahead now and actually write down our solution. So sine of u plus v equals sine of u is going to be 2 over the square root of 13 times cosine of v is 2 root 6 over 7 plus cosine of u is 3 over the square root of 13 times sine of v is 5 over 7. Now let's talk about what happens. There's a 2 times 2 root 6. Well, that's going to work out to be just 2 times 2 is 4, and then times square root of 6 cannot be simplified, changed, anything like that. It's just 4 times the square root of 6. And then the square root of 13 times 7, well, that's just the square root of 13 times 7, except we usually put the whole number first. So it's going to look like that. The next fraction is 3 times 5, well, that's 15, and then it's also going to be over 7 times the square root of 13. Now we can combine these. We'll end up with, we can't really combine something with a square root and something without a square root. So it turns into this sort of messy expression. You can plug this into a calculator, though. You would get a number out. It just kind of looks bad. So we'd end up with this. Now, unfortunately, this is not going to be accepted by Delta Math because there's another rule that comes up. And this is really just good practice in terms of rewriting expressions, which is a common math technique. You have to be able to rewrite expressions in different ways. If that doesn't convince you that you actually have to do that, the ACT and other standardized tests often have answers written in different ways. So you need to be adept at figuring those out. So the problem here is that we can't have a radical in the denominator. So all I'm going to do is multiply the numerator and denominator by that radical. So this is going to distribute to each term in the numerator. And then square root of 13 times the square root of 13. You could try that on the calculator, but that's just going to equal 13. So I end up with 15 times the square root of 13 plus 4 times the square root of 6 times the square root of 13, which I'll change in a moment. And then in the denominator, I end up with 7 times 13. If we keep this going, we're not quite into the simplest form yet. I guess it's debatable whether or not you think this is simple. 6 times 13 is 78. And then 7 times 13 is 91. So this would be our final answer. So what we did is we reduced any square roots, so that 24 up there, we reduced that. And then also you cannot have square roots in the denominator. So no radicals in denominator. And also reduce square roots if possible. For example, what I'm saying here is the square root of 24 equals 2 root 6. Or you could look at, I don't know, the square root of, let's do 18. That would be 3 times the square root of 2, etc., right? So if you have perfect square factors under the radical, you have to take the square root of those and take them out. Overall, this doesn't really bother me too much on a test because I know that you understand the math, what's going on. But in terms of just rewriting expressions, this is a really important skill to have, and it does come up on the Delta Math as well. Okay, so that was the first type of example I wanted to show you, just to kind of remind you about square roots, or to teach that if you hadn't ever seen that before. So let's go ahead now and let's go back to our regular situations without square roots, except now we're going to figure out tangent, because we haven't done a tangent yet, and tangents do get a little bit more complicated. So we'll do tangent of theta plus phi, and we're going to do, given, let's say sine of theta is negative 15 over 17, and we'll say that theta is in the range of, let's go with 180 degrees is less than theta is less than 270. So this is another way to say that it's in quadrant 3. And then we'll go with cosine of theta equal, cosine of phi, sorry. Cosine of phi is going to equal 8 over 17, where we'll say 90 degrees is less than phi is less than 180. So that's another way of saying that this is in quadrant 2. If you take a look at your unit circle, you'll probably recognize that. All right, so I have my two pieces of information. Let's start off this problem by reminding ourselves what the formula is. This is good practice on a test, is to start off by writing down the formula. So we have, at the very bottom left there, we have our tangent formula, tan plus tangent, and then 1 minus tangent times tangent. Just double check I did that correctly. Looks good. Okay. So we have no information yet about tangent of theta or of phi. So we're going to have to go ahead and create the triangles in this case. So theta puts me down here into quadrant 3. I know that sine is 15, so it's opposite over the hypotenuse. This has to be negative based on the quadrant it's in. And if you use the Pythagorean theorem to calculate for the missing side, you're going to end up with an 8 here. But it has to be negative because we're in quadrant 3. So this was 17 squared minus 15 squared, and then the square root. Okay, so there's theta. Now, I just realized after I wrote this that I actually made a mistake for phi. This really should be negative if we're in quadrant 2, otherwise it doesn't make any sense. So let's go ahead and do phi now. Phi is somewhere here, maybe in quadrant 2. And we're going to end up with kind of the same triangle. So that makes this easier. That has to be 15. Okay. So now that I'm writing this problem out, I think I messed up on phi now that I'm looking at my notes here. Let me go back and change that real quick. Sorry for the typo. Luckily, we haven't done too much work. So I want cosine to be, let's do negative 4 over 5. Okay. So here's phi. And I'll make a triangle with the x-axis, and then the adjacent side is negative 4. The hypotenuse is 5. That means that the missing side has to be 3. And so there are my triangles. Now we can go ahead and start plugging into our formula. So I have tangent of theta, so that's over here, negative 15 over negative 8. Which is really just positive 15 over positive 8. I'm now going to add tangent of phi, so that's over on this side, 3 over negative 4. And then in the denominator, I have to go 1 minus 15 over 8 times negative 3 over 4. And so now we have to do some work. We're going to go ahead and maybe I'll just annotate this real quick so we know where all these things are coming from. Okay, so in the numerator, we need to get a common denominator. So that's going to be 8. I'm going to subtract 6 over 8. And then in the denominator, I'm just first going to multiply. So it'll be 1 plus 45 over 8 times 4 is 32. In the numerator, we can rewrite that as 9 over 8. In the denominator, we'll have to convert the 1 to have the same denominator as the 45 over 32. We'll keep this going, 9 over 8 over 77 over 32. So I'm just working with that part now. In order to divide fractions, you have to multiply the numerator by the reciprocal of the denominator. And before I multiply, I'm going to do something which is sometimes referred to as cross-canceling. The 8 and the 32 share some common factors. So 32 divided by 8 is just 4. And that makes my multiplication a little bit easier. 9 times 4 is 36. And this is my final answer. So tangent requires a little bit more simplifying in terms of the fractions. So that's why I wanted to take a little bit more time with that. Just kind of review your fraction rules. We did some adding with different denominators. We did some multiplying, and then we also divided. So we basically did all the fractions in this one problem.